Now we know that we can find densities with the ideal gas law, or if we don't realize that, I'll point something out. If you take a hot air balloon and you let the hot air balloon start to cool down, what happens? The balloon sinks. Why? It wasn't less dense than air anymore. So, as a consequence, we should be able to use temperature and volume and all these other things and plug them in ideal gas law and find densities. Now, if we can find density where we're finding out mass and we know the number of moles, we should also be able to determine the molar mass. And so let's set up an ideal gas law derivation that allows us to work with density and molar mass. Now, let's just remind ourselves that density equals mass divided by volume. Easy enough. Well, mass is going to equal the number of moles times the molar mass. We know that one too, right? And we can go ahead and get the ideal gas law ready for us to do some substituting. So you can see PV equals nRT. We've got N. What we want to do is substitute in molar mass and our mass and play with it a little bit. So if we do that, we go ahead, we rearrange this so that it's N equals mass divided by molar mass. We substitute that in, we get PV equals mRT over molar mass. Next up, we can go ahead and rearrange this just a little bit more by realizing that mass divided by volume ends up being density. So density pops in right there. Now you want to know that, or you want to be able to derive it. It's easier to know it. And so the way that I like to remind people of this equation, PM, like the evening, DRT sounds like dirt or desert, so I like to describe it as being nighttime in the desert as the mnemonic for it. Now, the takeaway message for all of this, as you increase your pressure, you increase your density. That seems reasonable, right? If I take a gas and I compress it, the same amount of mass is going to be compressed in a smaller space. Molar mass, if it increases, so does your density. Again, that should make some sense. The ideal gas law is independent of the identity of the gas. So I can increase the mass of each of those molecules without changing anything about ideal gas law. As I do that, I'm increasing the mass in a certain volume, and so does density. Both those will increase. And just like I pointed out with the hot air balloon, as you increase your temperature, you decrease the density. Hot things can float. Cold things will sink. And we see that with liquids as well, but it's more pronounced for gases for certain. So that's one of the takeaway message sets that we can use for the ideal gas law once it's been derived to use density and molar mass.